Switches are very different from hubs. There are also called Ethernet bridges. The switch configuration is the most used configuration. These days you don't even see hubs. All machines are connected through switches. What does a switch do? Basically it transfers frames from an input to an output link. Well, this is what a hub did, but a switch can buffer packets. Not only that, a switch runs a MAC protocol on each interface. For example, if you look at this equipment, this has 48 ports. By ports, I mean it can support 48 hosts, and on each of that interface connecting to a host, it will run a MAC protocol, which is the CSMA-CD. One big advantage of switches is that they can help break up the collision domain. I will show an example shortly. Switches can switch speeds also. For example, if this is being connected through a 10 Mbps link, you can potentially switch the speed to 100 Mbps. This is possible because it buffers the packet and then again transmits the packet on this other link using the media access control protocol corresponding to that link. So here is interconnection with the switch. Notice that there are 3 hubs which are connected to a switch, and remember that a switch on each of these interfaces, it is going to run a media access control and it isolates these. Given that, how many collision domains does this particular topology have? That's right, 3 separate collision domains. For example, if this host has a packet to send to some other host here, all it has to worry about is to send the packet to that particular switch. So it is going to compete with the switch and as well as this other host to transmit the packet. Once this packet reaches the switch is going to buffer the packet and then it is going to again contend with all these other hosts as part of this collision domain and going to send the packet to the designated destination. Just to emphasize, this collision domain has 4 stations, 1, 2, 3, as well as the switch competing for access to the media. Once this packet reaches the switch is going to compete again with these 3 other hosts to access this media to deliver it to the right destination. So use of switches can significantly increase the reach of the network. For example, if you were employing the 10 base T, as I said, there is a restriction of only 500 meters here. But if you interconnect it through a switch, you can potentially span few kilometers. So a question should have popped in your head as to how does the switch route packets. We will cover all this as part of Ethernet switching in another video. When you employ switches, there are 2 modes of operation. One is the shared mode, which is also called half duplex mode, and in this mode you employ the media access control protocol CSMA-CD. So this is an example where the switch is operating in a half duplex mode. A switch can also operate in a full duplex mode. In full duplex mode, each station is connected to the switch using 2 pairs of wires, one for transmitting and one for receiving. Basically, this link is going to be a full duplex link. Given this, do you see there is a need for media access control here? That's right, there is really no need for media access control because this is like a point-to-point link and there is no one competing against this particular link. By the way, the same topology could also be supported in half duplex mode where this link is a half duplex link, and there is going to be contention there because to access this link you have the switch as well as the station trying to compete, and you have to resolve contention between the switch and the host. Whereas in a full duplex link there are 2 pairs, thereby there is no contention. Ethernet as such provides what is called a connectionless service. By connectionless, I mean that the sender and receiver do not do any handshake before transmitting the packet. So the sender, whether the receiver is alive or not, will just send a packet. It doesn't care about the status of the receiver. Whereas if you typically employ handshaking like in TCP, you ascertain the status of the receiver before you send packets. But Ethernet as such is a connectionless service. Not only that, it is an unreliable service. In other words, it does not provide any means for recovering lost frames. If a packet is lost due to errors, it does not implement any reliability. If you want reliability, you need to employ TCP at the higher layer. Just to clarify a point here, I mentioned earlier that random access protocols, whenever they see a collision, do retry later to retransmit the packet. That is not the same as providing reliability. If your media access control protocol didn't even recover from collisions, it wouldn't be much of a media access control protocol. So you do need to recover from collisions, but you don't have to recover from errors resulting from high noise or crosstalk or interference. So here is the Ethernet frame structure. It has this combination of preamble and SFD. It can be viewed as a sentinel, which we covered as part of framing. The preamble is nothing but a sequence of alternating ones and zeros, mainly used for synchronization. The SFD is also a series of ones and zeros, except that it ends with 1 1, just to show that this preamble has ended and the header has started. Following the preamble is the destination address and the source address. These are 48-bit long. This is also called the MAC address, often expressed in hexadecimal like this. If you want to know what the MAC address of your Ethernet adapter is, if you type ifconfig eth0, you will see this is in Linux. If you're in Windows, if you do ipconfig, you can figure out what the MAC address of your Ethernet adapter is. The type field is a demultiplexing key. Basically, it specifies which higher layer protocol this packet has to pass to, IP or ICMP or so on and so forth. After the type field is the IP payload. Again, this can take values between 46 bytes up to 1500 bytes. Notice that there is a minimum size requirement. Why? Again, we will cover as part of the MAC protocol. And after the data is the CRC, which does error detection. Another thing to note is you have to maintain a gap of 96 bits or 12 bytes between two frames. This is basically to ensure that the receiver has enough time to process this packet before it can receive the next frame, like empty the buffer and so on. So let's quickly also look at the Ethernet addresses. Each adapter has a unique address. Note that I'm not using host. Host can have multiple adapters. Each network adapter has a unique address, and this uniqueness is basically ensured by giving each manufacturer a different prefix. So for example, if Intel is manufacturing these adapters, this is the prefix that it will use. In normal mode, whenever an adapter receives a frame, it passes up the frame if the frame is addressed to it. This is the unicast mode. In other words, it will see whether the destination address in the frame matches its own address. If so, it passes up the frame. It will also accept the frame if the address is broadcast address. Broadcast address is nothing but all ones. This in hexadecimal will turn out to be all FFs. It will also accept a frame with a multicast address if it belongs to the group. In multicast address, the first bit is always 1. And you have to configure your adapter to accept frames corresponding to this multicast address. So that's more or less what is to know about the Ethernet technology. In summary, Ethernet underwent significant evolution over the years. It started out with 10 Mbps. Now we are dealing with 100 Gbps Ethernet. The speed increased by 10,000 times. Ethernet operates over a variety of media. I mentioned coaxial and twisted pair. It can also work over fiber optics. It went from bus topology to star topology. Within the star topology, originally hubs were used, but with the use of switches, this even circumvented the need for a media access control. So these days, there is no media access control used as part of Ethernet. So there are many standards that cater to the various versions of Ethernet. For example, 802.3i is the 10 base T standard, 802.3u is the fast Ethernet standard, 802.3ab is the gigabit Ethernet standard, 802.3x is the full duplex standard. If you look up in Wikipedia about the number of standards 802.3 family has, you'll be amazed by the range. The only thing that has remained constant in the evolution of Ethernet is the frame format. Going forward, we will look at the media access control employed by Ethernet, basically CSMA/CD. This is applicable only in the shared mode, that is the half duplex mode. This is not applicable in the full duplex mode.